Hello, my name is Evan Zabowski. I'm the Senior Technical Advisor here at TestOil, and today's quick little webinar is on the root cause of an overheated gearbox. What I'd like to go through today is give you kind of some snippets of what we cover in our comprehensive training. So to begin, I'm going to go through a few excerpts that we cover within the training section, and then I'll show you a case study of an overheated gearbox, and then walk you through a couple more excerpts and get to the final verdict. So with this, I'd like to begin with a quick excerpt from our lubricant function section. One of the things we discuss is, well, why do we use lubricants? What is their purpose? And of course, the number one reason that we use lubricants, the number one thing that we're going for, is to reduce friction and wear. So one quick little definition I like to show is the definition of friction. Friction is simply defined as a resisting force. And the thing about friction is not all friction is bad. Some friction is actually desirable. Without friction, we don't have as much control, right? You think of something as simple as driving. You need traction to get going and you need braking to come to a stop. But when we think about friction, friction comes in many different modes. The two primary types of friction are generally considered to be static and kinetic. However, kinetic friction can be broken down into three subcategories. We have sliding friction, which is common in anything that reciprocates, or of course journal bearings. And then we have rolling friction, which is in anything that rolls, typically rolling element bearings. But it's that third friction that we sometimes forget about, that we don't always consider, and it's called fluid friction. And it is the resistance that any of the moving parts encounter due to a liquid or a gas. So this is one of the reasons we don't fill gearboxes all the way to the top with oil, is because it's harder to turn the gears in oil than it is to turn them in air. So we're always looking for just that minimal layer of lubrication that satisfies the needs, and that helps us to keep as much friction out of the equation as possible. Now, another quick little excerpt I like to get into is lubricating oil films. Now, when it comes to lubricating oil films, they're generally defined by something that's known as the film thickness or the lambda ratio. And most correctly, it would be called the specific film thickness. But the lambda ratio does a pretty decent job at explaining to us that at least it's a ratio. However, what is lambda? So lambda is a Greek symbol to represent this ratio, and the ratio is the fluid film thickness divided by the surface roughness. So when this value is very, very low, like less than 1, we have what we call boundary lubrication, meaning there is metal-to-metal contact at all times. When lambda is a little bit higher than 1, but less than 4, we consider this to be in the mixed lubrication regime, meaning there is no metal-to-metal contact always, but there will be intermittently. Once lambda reaches a value of greater than 4, this is the regime we call hydrodynamic, and this is where we consider it to be full film lubrication, fully separating the moving parts from each other, meaning there is no contact, or should not be any contact. And all of this is exemplified by the diagram called the Strybeck curve. Now, the Strybeck curve shows us a graphical representation of friction as it compares to various lambda ratio values. So you can see here on the left-hand side that we have very high friction at relatively low lambda values, and this continues to be fairly flat until we reach a lambda value of approaching 1. Once lambda approaches 1, the friction begins to drop. Now, as soon as lambda reaches a value of 1, it drops significantly. And this will plummet until it reaches a lambda value of approximately 4. At this point, you've reached the lowest attainable friction. Any lambda value greater than 4, you will see a slow and steady increase in friction. And this is kind of a clue as to where we're going later with this discussion. But without further ado, let me present the overheated gearbox. So consider that you have a gearbox that is overheated. Now, these are not the actual FLIR images from the gearbox, because if you look closely, you might come to a different conclusion. I just needed a way to show a gearbox that was hot. The thing is that when you see an overheated gearbox and you know that you have one, you would use a very quick diagnosis to come up with some simple things to check or eliminate. And so typically you use your 5 senses. Now, if you were to go out and visit this gearbox with your 5 senses, what would they tell you? Well, with your eyes, you might see something regarding the oil level. It could be too low, it could be too high, it could be just right. Not to sound like Goldilocks here. But one of the things you might notice is that the oil is quite dark. And if it's quite dark, you might have a clue as to how badly it's overheating. But another thing you can see with your eyes, and this depends on the installation, is you might have a magnetic plug. And if you had a magnetic plug, you could check it for any wear debris. Now, while you're looking with your eyes, you can feel with your hands. So what are you going to feel? Well, you will definitely feel that it's hot, of course. But one of the other things you can check for is vibration. If it seems to be vibrating, then that may give you an idea that there's an imbalance or a misalignment, and that could be causing the overheating. Now, if we continue along, you might hear some noise. This may be directly related to that vibration. Right? When we say noise, we just mean louder than it normally is. Other than that, your nose, you might actually smell the burnt oil. You might be able to detect that the odor of the gearbox is actually from a high enough temperature to cook the oil to a point where it will start to smell actually burnt. And if you're looking at tasting the oil, well, that's an HSE violation. Please don't do that. That's just a little bit of humor here. But understanding that we have this overheated gearbox, understanding that we would probably go out and check it out for ourselves, here's the issue. We go out there expecting that the oil level is low, and what we find is that's not the case. It's neither too low, too high, nor is it anything abnormal. It is exactly where we think it should be. So we've eliminated a couple of obvious choices, that it's not boundary lubrication from too low of an oil level, nor is it necessarily fluid friction from having too high of a level. We take a listen. Now, if we listen to this gearbox from time to time as we walk by, we'd have a rough idea how loud it normally is. And in this case, again, we're not going to say that it's abnormally high for volume. Next, we go check it out with our hands, and we place our hand on it to see if we can feel that vibration. And again, what we're noticing is no significant vibration, no more than is normal. So at this point, you're wondering, well, if we didn't find anything, then what's the issue? And this is kind of the fun part about data interpretation, is that sometimes it's not what you see, it's what you don't see that tells you what you're looking for. Give you two quick examples. One is the classic story of Sherlock Holmes and the Adventures of Silver Blaze. That is the name of a racehorse that gets stolen and its owner is killed. So Holmes is sent out there to do the investigation to see if he can figure things out. Now, after he's collected his clues and interviewed a few people, he meets up with the inspector, and he asks him this question. He says, "Is there any other point to which you wish to draw my attention?" Holmes's reply is, "To the curious incident of the dog in the night." Well, during his interviews, one of the things he discovered was the dog didn't bark. So Holmes's reply kind of puzzles Gregory, and he says, "The dog did nothing in the nighttime." And Holmes's reply is, "That was the curious incident." What Holmes has realized in this story is that because the dog did not bark, the person who stole the racehorse must be familiar to the dog. And therefore, Holmes concludes it was an inside job. And as it turns out, not to spoil it too much for you if you ever care to read the story, but it was the horse who killed the owner because it was, of course, protesting it being taken in the middle of the night. But like I said, it's what we don't see that sometimes tells us what we should be realizing. The other classic example, and perhaps you've seen this image come up on social media, this is an example taken from the Second World War where they were investigating plane damage as bombers returned from battle. And statistician Abraham Wald was doing this investigation, and he was trying to show how we bias some of our decisions based on data. And in relation to this one was where to put the armoring. So if you had to pick 4 places on this aircraft to add additional armor plating, where would you do that? Right? A lot of people would pick a wingtip, right? And of course the other wingtip too, because it's just as damaged. Then they'd pick the fuselage over the wings, and they'd probably also pick the tail section. And Abraham Wald's argument was he would pick none of those regions. In fact, his 4 primary areas, he said he'd definitely pick the cockpit. He'd pick both engines, right? Each engine, and he picked the fuselage in between the wings. These were all areas that he felt needed armoring, and his logic was that every plane that returned with this damage, and you can see, from the diagram all the holes, those were planes that actually made it back. His point was that if planes got shot in the other 4 areas, well, they didn't make it back. And so if you really wanted to help, preserve the fleet and win the war, you had to, of course, armor plate the regions where there were no holes. That's why I say it's holes in the data. But anyways, to get us back to the Strybeck curve, now that we've eliminated too low of an oil level, we've eliminated noise, and we've eliminated vibration, what do we know about where we are on the Strybeck curve? Well, what we've learned is we're probably nowhere on the left-hand side of the Strybeck curve, because that would indicate a low oil level would cause boundary lubrication. A misalignment or an imbalance would also cause metal-to-metal contact. So there's probably no way we're in the boundary or the mixed region of lubrication. Where we are, however, is somewhere in the hydrodynamic region. So now let me give you another quick little excerpt from our comprehensive training program from the lubricant analysis section. In this section, we discuss quite a few different tests and the results of those tests and what they mean and how to interpret them. But what we begin with is just a quick, simple overview of the most common degradation mechanisms. And for lubricants, it tends to be oxidation. Any reaction with oxygen will cause the oil to form acidic byproducts, sludges, varnishes, all these nasty things we don't want. These reactions are accelerated by things like heat, water, wear metals, all kinds of different things. So it's very common that you will expect to find oxidation. It's just a matter of what rate it's happening at. And when that rate gets excessive, well, then bad things start to happen to the lubricant. Most commonly is that the lubricant will darken and it will build up acids and varnish precursors and whatnot, but you might also notice a burnt odor. So that's one of the reasons that we would go out with our 5 senses to check these things, because if the oil looks darker than normal, we know the oil is being damaged. If it smells burnt, well, frankly, it is burnt. So one of the other things we get into, like I said, is the testing and the results. So one of the tests that I would cover is infrared. And in infrared, we measure things like oxidation. So when oxidation is measured, one of the key things to note about this is what drives it. Well, like I said, it is a degradation mechanism, so it is expected. But the point is, what happens if it gets excessive? Well, that's because something accelerated it. So with oxidation, it tends to be heat. And with heat, if you have heard of this before, the Arrhenius equation estimates how much a rate of reaction will take place at a different temperature. And for many lubricants, that roughly works out to a doubling in the rate of reaction with every 10 degrees Celsius, 18 degree Fahrenheit rise in temperature. So given that the bulk oil temperature of this gearbox is higher than normal, right? That was our first, sort of clue, was that we knew we had an overheated gearbox. Well, then we can expect that there will be some damage. But as we go through this oxidation section, one of the things I mentioned is you can tell how bad the oxidation is by seeing if there's nitration in conjunction with oxidation. When you have oxidation and oxidation only, the temperatures don't tend to be that high. They're high enough that, of course, they accelerate the rate of reaction, but they're not really that harmful unless they're left for a prolonged period of time. On the other hand, when you see oxidation increase at the same time as nitration, that tends to indicate some abnormally high and maybe very localized hotspots within the system. And that tends to indicate the worst of the type of oxidations. The last thing I like to cover about oxidation, though, is a pitfall. How do people commonly misinterpret oxidation? And the big point I make with this is not everyone knows what it looks like. So people tend to forget what it looks like, and really the basic description I can give you for oxidation is it is very, very dark. You would not describe this as a reddish or brownish color. You would describe it as very dark, dark, dark brown, if not outright black. But the other thing is its physical appearance. Not only is it black in color, but it actually has a texture to it. It tends to form granular, gritty particles. And that is another big clue to look for when you're taking oil samples. Not to say that you need to rub them between your fingers, that doesn't always tell you that much. But if you're pulling something like a filter or a strainer, this is where you would see a buildup of this kind of debris. And again, you could check it by running it through your fingers. If it was nitration and nitration only, it actually feels quite tacky and sticky until it builds to kind of a sludgy, slimy feel. So nitration is actually quite a bit different than oxidation, even though the two are closely related. But one of the key benefits of taking the course is where it comes right at the very end when we cover a section called How to Read a Report in 2 minutes or less. And I won't go through the whole thing here, but we do cover the mechanics of getting through a report quickly and efficiently. And in this section, we cover that step one is simple. It is read the whole report, read all the data. And that's something not a lot of people do. And when I say all the data, I don't just mean what the laboratory came up with. I mean, what did you tell us about the machine in the first place? Step two, though, we move on to, as we go through the actual laboratory data, deciding what data looks abnormal. And when we decide it looks abnormal, whether it's too high, too low, too far from the baseline, too far from the previous sample, whatever the reason is, all I ask is that you classify that data as either a cause or an effect. And the point is that by the time you get to the end of the report, you'll have grouped all your causes in 1 or 2 groups, and everything else in the report you saw was merely an effect of those causes. Step 3 then is to decide what to do next. Right? How do you address these causes? So to give you a good example here is an oil analysis report from an overheated gearbox. And just to remind you, this is your new oil line, so there's your baseline information, followed by this section over here is actually the current sample we'll be looking at. But if you look closely at this report and you read all the data, you will see some different clues that maybe you don't always pick up on. So one of the key things that I look at is, like I said, read the whole report. So you start in the very top. So it tells you it's an industrial gearbox. It tells you it's got a 110-gallon sump size. You know it's a pretty big gearbox. You read down, you see what kind of oil it has. Unless you're familiar with the Alcoa product line, you might not know if that was an EP or what grade it is. But you try and familiarize yourself with what you're expecting to find. As you keep reading the report, you're going to eventually come down to the comment section here. So you'll see the problems listed on the left, and you'll see comments related to those problems listed to the right. You can read through these, and you'll get a fairly middle of the road kind of interpretation that the lab came up with as to what's going on here. But you notice in this particular example, it says high oxidation, viscosity, acid number, and particle count. Quite a few things they found wrong. Now, as you start reading the report, like I said, don't immediately jump down to the data. Read here, you can see sample dates. You can see it was sampled monthly. You can look at the hours on the oil and the hours on the machine. You can see that they're accruing at the same rate, meaning that there's been no oil changes. And there seems to be roughly 700 or so hours every month. So this looks like a pretty continuous duty type application. From that, I have an idea what I'm expecting to find. I'm expecting then, without any resets to the oil life as compared to the machine life, meaning no oil changes, that every trend should be smooth and steady. Whether it's up or down or just level, there's no reason to expect it to take a sudden jog in a different direction. So now once you get down to the actual data, you start pointing out the things you find abnormal. So some people might pause on iron, but really if you look at the iron values, they're bouncing around and they're slowly but steadily increasing. Copper happens to be even a flatter curve than that. So no, the wear metals are nothing significant. You go through down to the additive section, and though it doesn't match base oil, they've been very, very steady. So again, I don't see any issues on the first page here. Once we get down to the bottom half of the first page, though, we may see some data that does stand out. And so first and foremost, and it was already identified in the comment section, there is high oxidation. So that is something we would consider abnormal, and I would simply ask, is it a cause or an effect? It's an effect, right? Probably heat caused it, but let's just leave it at that. You may pick on nitration and say that nitration is also high because it is higher than the baseline value, and that's a fair comment one way or the other. If you want to argue that it is abnormal and therefore should be considered, or if you want to say, well, it's been flat and steady and we don't need to consider it. But just for a moment, if you did think it was abnormal, it still is just an effect. It is not a cause. You keep reading down to the report and you can't help but look at the particle count and see that it's very, very high. So again, is that a cause or an effect? Well, I'll give you a hint here. It's an effect. Right? If the particle count was high as a cause, it should have led to the increase in wear metals, which it hasn't. So the particles that are appearing in the particle count, probably the result of some of the chemical reactions we're seeing. That is further evident by the next thing that we see abnormal in this report, and that is namely the viscosity. Looks like it should be about a 460 oil, but really it's a 680 or maybe even higher. So this oil is way too thick for what is being apparently called for. And again, is that a cause or an effect? Well, if it was fairly steady, if it was a flat set of results and it was right on par with a particular grade of oil, you might think it was actually the cause. But considering that it's slowly but steadily increasing, it shows us that something's happening to the viscosity, which clearly indicates it's also an effect. Last but not least, the next abnormal thing on this report would be the acid number. It has climbed quite steadily and is showing us that it is significantly high. And again, is that a cause or an effect? Well, it's just an effect. Something is making that acid number climb. So when you get to the end of the report and you look at your final tally, you're going to see that everything we identified, oxidation, particle count, viscosity, and acid number, those are all just effects. We didn't really find anything on the report that identified itself as a cause. But the point is, once you get to the end of the report and you look at these, you do not focus on the effects, you focus on what is the cause. And really all of those have one common denominator as a potential cause, and that is namely, of course, the heat. So we're right back where we started from. We had an overheated gearbox, we looked through the oil analysis results, and all we could conclude was it's overheated. So we haven't really made much progress, so it seems. But this is why I'll remind you, and I did plant this seed, why do we go through things like talk about lubricating oil films, right? To refresh your memory, right? The Strybeck curve. We talk about this because we know from our other data that we collected from a visual inspection, we're not on the left-hand side of the Strybeck curve. We must be over on the right-hand side of the Strybeck curve. So if we've got too high of a friction causing the gearbox to overheat, where are we on the Strybeck curve? Well, we're way too far to the right. So what do we need to do? We need to move to the left. So how can we move to the left on this Strybeck curve? Well, if you look at the calculation, you can see that it has a few things that maybe we could modify, like speed or load, but ultimately those are usually set by production, and we have to just deal with it. Well, surface roughness is another thing that's pretty hard to go in there and change all the roughnesses to something that's smoother perhaps. So what can we do? Well, namely, we can change the viscosity, right? That's the key thing we can do. So getting to this point of the discussion, you're about to fall into a trap if you're following along here, because my question is this. If these were the only two oils you had on site suitable to go into a gearbox, a 220 and a 320, right, those are isoviscosity grades, which of these two oils would you think would get you the better result? Lower your heat, decrease your friction, whichever way you want to look at it. But which oil do you think would actually fix the problem? And I'm wagering many people are looking over on the left-hand side there at the 220 thinking, well, according to the Strybeck curve, we need to go to a thinner oil. And you know what? That logic is sound. That is very good logic to have. You do need to go to a thinner oil. That would reduce the friction. Question is do you know for a fact the 220 is thinner than the 320? Right? And a lot of people say, well, of course it is. It's a whole grade lower. And you go, well, here's something else though. In our lubricating oil properties, we spend a great deal of time discussing viscosity. And one of the key things we know about viscosity is it is affected by temperature. Right? Most people are pretty well aware that the higher the temperature, the lower the viscosity. But one of the things I like to point out about viscosity is that change is not linear, meaning it does not follow a straight line. It's kind of a curved line. But the even more important thing I like to point out about viscosity and its reaction with temperature is it's not the same for every oil. Meaning you can take two oils of the same viscosity at the same temperature and heat them up the same amount, and one will thin more than the other. So this becomes an issue when you think you know where the viscosity is going to be at other temperatures, and you make these false assumptions that it follows either a linear relationship, that for every 10 degrees you heat it up, it thins by the same amount, or that two different oils thin at the same rate. Those are both common misconceptions and can both lead you, to an issue. So just to show you an example, I've plotted here a 320 and a 220 on a viscosity temperature curve. And you can see at room temperature of 20 degrees Celsius, roughly 70 degrees Fahrenheit, that sure, 320 is definitely thicker than a 220. But as you start moving to the right along this chart and seeing higher and higher temperatures, and you get to a normal operating temperature of about 160 degrees Fahrenheit, which is 70 degrees Celsius, you see that these two oils become the same viscosity. Now, any temperature that was over 160 degrees Fahrenheit, 70 degrees Celsius is probably something we would consider to be hot. So going back to our beginning statement, if you walked up to a hot gearbox, right, probably at a temperature over 160, if you decided to switch from your 320 oil to a 220 oil, what would you have done to this situation? Right? You'd have made it worse. Because at those temperatures, anything above 70 degrees Celsius, 160 Fahrenheit, given these two oils as choices, the 220 is actually thicker than the 320. And this is one of the most common reasons people have these apparently unsolvable issues of overheated components, where they're like, nothing else seems wrong, right? There's no misalignment, there's no imbalance, there's no issue with the lubricant levels. You know, people even talk about they've switched to synthetic lubricants and they just can't get the temperature down. One of the key things to look at is, do you have the viscosity right? Do you have the correct viscosity for the operating conditions that you're undergoing right now? So there's just a quick overview. Like I said, it was meant to be nice, sweet, and short. So I do thank everyone who has been watching. I greatly appreciate the time you took. We are doing these again tomorrow and Thursday, and then all of Tuesday, Wednesday, Thursday of next week as well. Just again to showcase some of the things that we cover in our comprehensive training and show you how they can really benefit you with some of these common everyday concerns. So with that, I'll end the presentation here, but I'll look into the chat and see if anyone's throwing some questions in there. If there are, I will address them. If not, I will end the presentation after about 30 seconds of silence. So again, I thank you for participating.